Welcome to the first video of the IFIMAC colloquium series. Today we are interviewing Andreas Heinrich. He's currently the director of the IBS Center for Quantum Nanoscience at EWHA Womans University in South Korea. What is it that you do? What's your research about?
All right, so I like to work with single atoms. And so if you think about what does that mean? So the smallest thing that you can ever build something with, if you cut your block of Legos down and down and down, you're going to end up with single atoms. And so you can ask yourself, can we start with single atoms and build structures one atom at a time? And so over my many years of research experience, kind of the one theme is always build stuff with atoms.
And how do you do that? What techniques do you use for that purpose?
So, you probably learned somewhere in school or something that you cannot see an atom, right? An atom is too small. And that's correct. An atom, you cannot see an atom with a normal optical microscope because it is much smaller than the wavelength of that light. So you need specialized tools. And so in my case, the tool is called a scanning tunneling microscope. That's a little bit complicated word, scanning tunneling microscope, or an STM. That allows you to really see atoms, one atom at a time, not inside the material, but only on the surface, on the top of that material.
You use STMs for measuring single atoms. You can modify them. What's the purpose of that? What is your goal with this microscope and those atoms?
Right. So, okay, let's say you can build stuff with 1, 2, 3, 5, 10 atoms, right? What can you do with that, right? And so I kind of look at this in two ways. One, I feel like I want to explore, right? I don't really have a goal. I say we can do something new. Let's say we have a better resolution. We can see things that are much smaller, finer. And let's see what we can find. This is kind of like the old explorers. And the other part, of course, is a bit more directed. Like you want to solve a certain problem, right? And that particular problem that we are interested in right now is called quantum computation. In order to do quantum computing, we need a little bit more, right? The technical term for that is electron spin resonance. The best way to explain electron spin resonance, I think, is to look at where you may have seen this in your normal life, right? And that, unfortunately, is kind of a negative thing. That's magnetic resonance imaging. If you break your bone, you go to the hospital, and they'll do an X-ray, but they also do a magnetic resonance imaging where they look at the nuclear spins in your arm, particularly the ones in the water related to you, I guess, right? And then they can image this by using a concept called magnetic resonance. And that magnetic resonance takes the little magnet that is your hydrogen atom in the water, and it spins it around in a very controlled manner. And this spinning it around in a controlled manner, that's called magnetic resonance. And so what we learned, about 7, 8 years ago now, is that we can do that also with a single electron, the spin of a single electron of our atoms on the surface. So we can do that with a single spin, and that allows us to do this quantum computation.
We think that for you it is very important to let the world know what you know, because we've seen the tutorials you have on your website.
It's extremely important to communicate science to a broader audience. Right? Why? Because it helps you understand what you do. Right? If you cannot explain your science to your grandmother, then maybe you don't understand your science enough. Right? Maybe you have to start explaining what an atom is. Right? Or maybe you can go to elementary schools and explain this stuff. Right? They get excited, and I just love see the excitement in people's eyes.
See, everyone knows that you're one of the people that made the smallest stop motion film ever, The Boy and His Atom. How would you say it was the experience for you in particular?
Then I was working at a company, right? The company has clear goals. And if you do basic science in a company, you have to prove to the company that there's some value in basic science, right? And in this case, I was approached by IBM and IBM's marketing firm, Ogilvy, to make this movie. And there was actually a real goal. The goal was to make a YouTube video that had the most views of an IBM produced video. And that was 1 million views, right? So the goal of this video was, let's make something that is so interesting that 1 million people would watch this, right? So we did such a great job in the end that 1 million views was one day. Why did I do it? Because I like the aspect, if you look at the comments on there, right? They are all very good. they're good positive comments. Is it an atom or is it a molecule? Or, you know, wow, that's amazing, that's small. Didn't know that people can do this, right? So it's very heartwarming to see that people care and people want to understand this, right? And they put their effort and their brains in to really try to understand what this is, right? And so this helps maybe people to be more interested in science and engineering, and that's a good thing.
What would you say to encourage someone that is thinking about studying physics?
Now, if they come to me and said, say, Andreas, I'm interested in physics. Do you think it's a good idea to study physics? Then I would say, yeah. Why? Because physics is so broad, right? You can do astrophysics if you're interested in that, or you can do condensed matter physics, right? You can do data science derived. You can do theoretical modeling. Follow your curiosity, right?
How did you first got interested in physics?
I have to say I had a really excellent high school physics teacher. So I had the higher level physics course, right? And that was amazing. I really have to say I've never heard from anybody else who had such a great course. Why? Because it wasn't teaching the equations or something. It was like, here's an experiment. We were a small class, maybe 10 students. Come forward, do the experiments. Change this parameter, see what happens. Change this parameter, see what happens. How would you make a formula from this? Would this be in the numerator or in the denominator? What do you think, right? Is it squared or not, right? And then we would come up with some idea, and then he would explain what the real, explanation for this is. And that was really an amazing experience to get that, right? So I think I give credit to that high school teacher because of really excellent teaching skills to get me interested in science, right, or in physics in particular.
So thank you very much, Andreas, for being with us today.
Thank you.
And it's been an honor to have you as our first invite.
Thank you so much. Thank you.